So in the previous lecture, we completed our discussion on distillation column. So essentially what we did, we segregated this column into three parts. We said we have the top column rectifying section, bottom column we had stripping sections, and we had the feed here. Okay, so we made three balances for energy and species balance. One was for the top column stripping section including condenser, and the bottom we had the rectifying stripping sections including reboiler. All right, and then we made the overall balance including feed, top product, and the bottom product. And then we had this HXY diagram, Ponchon-Severett methods, where we marked all the selling points. We calculated how many number of plates are required to achieve that much of purification for the top product and for the bottom product. We also talked about reflux ratios, right? The reflux ratios is quite important. If you vary the reflux ratios, the number of plates required or the trays required in the distillation columns are also different. Okay. Then we had this total reflux, two extreme conditions, total reflux and the minimum reflux ratios. Okay. And then we had one more important point is where is the feed entry, at what tray or underneath what tray feed makes the entry. We are also supposed to mark that point. Now we address the last part through an example here. So we take up an example into the today's lecture, and where we calculate the reboiler load, condenser load, how many number of plates are required, and what is the feed entry. Okay, so let's look at the first example on this distillation column. So this is on Ponchon-Severett method. All right, and what we have done so far, we had a rectifying section including condenser. So we made energy balance and species balance. Okay, then we did the similar exercise for stripping section with boiler. All right, then we did complete, we made the balance on complete section. So we had the feed, we had the top product, and we had the bottom product. Then we talked about tie lines or the stages plus operating line. All right, then the last what in the last class we had the last topic, this total reflux, and we had the another extreme case, minimum reflux. All right, so today's lecture we take this example here. So we have a distillation column. Let's draw distillation column. Okay, the problem statement reads that feed consists of binary components of ethanol and water mixture, and it reads 30% weight by weight. So we can say ZF standing for XF or YF, it's 30% weight by weight. We will see how we'll make this calculations here. Temperature is given 40 degrees centigrade. Feed flow rate F is 5000 kg per hour. Okay, now it says the top product is withdrawn G. Let's mark these points here. So we have the first stage 1 here. So this is G1, Y1, HG1. So these are specks of the vapor which arrives at this condenser. The problem reads it's a total condenser. That means we condense the entire vapor to this liquid. So our top product which leaves here is a liquid D. So we have this XD and we have this HD. Now it reads the reflux is at bubble point. All right, so all it means this liquid or the product here D and the reflux L0 which goes to the column top here it's saturated. So first thing, if you recall from a discussion on this total condenser, Y1 will be same as xt and xt will be same as x0 because it's a total condenser. All right. Enthalpy Hd and HL0 will be the same because same product you are withdrawing here and the fraction of it goes back to the distillation column. Now this Y1 which arrives here at this condenser will be at some temperature which will be different from the condenser temperature. So here we must understand that from our previous discussion, the Y1 which is leaving from the top column, this will be in equilibrium with the liquid which leaves this top column. So if this is Y1, this is now X1. X1 is different from X0. So the temperature of this top column is also different from the temperature of this condenser here. In other words, even if the problem is bubble reflux is at the bubble point, this Y1 which we have here, this vapor which arrives here, is not at equilibrium with this liquid, right? So Y1 and X1 or X0 here, they will not lie at this tie points. In fact, Y1 is in equilibrium with this X. We will talk about this and we'll mark. We have to be very careful with the statement here. All it means reflux at the bubble point means this X0 or Xd will lie at the saturated liquid enthalpy curve. Okay, so that's one thing. We'll come back to this. Reflux ratio is given as 1, so R is 1, and from our definition of R is nothing but L0 over D. So this is L0 and this is D here. All right. Now we have this bottom product. So this liquid which trickles from the top, part of it is vaporized and sent back to this, the last column, last plate, which is NP. So the specs for this vapor would be G NP plus 1. NP plus 1 stands for a theoretical plate for this boiler. Then we have Y NP plus 1 and we have H G NP plus 1. And this vapor now will be in equilibrium with the top bottom product W, mole fraction XW and HW. So this vapor and liquid, they are in equilibrium. Just like this vapor and the liquid, they are in equilibrium. Not this vapor, not with this liquid. Although this condensation takes place at some condensation temperature Tc here. So similarly, there is a T1 here. At this T1, this vapor is in equilibrium with this liquid which is leaving. Not this vapor is in equilibrium with this liquid which is at this temperature Tc. Okay. So and similarly for this liquid, here we have the specs LNP, YNP, and we have HNP. Now it's very important that any of the problem like this we mark and give some nomenclatures here for NP plus 1, NP last plate, or we have Y1 here, so this is X1, so this will be L1 here, and there will be HL1 here. So at least for the top plate, for the bottom plate, for the feed, ZF, etc., we mark these points here. All right. Now the compositions, it's given here 30%. The first thing we should note here, it's given as weight per weight. All right. So we have to convert all of this quantity into moles, mole fractions. That's the way we have to do it, because enthalpy diagram, HXY diagram, are mostly given in this mole fractions. All right. If it's given in the weight fractions, then one can work on these quantities. But in this problem, we are going to give HXY diagram, all of this in this mole fractions. So we have to convert all compositions for the feed or for the top and the bottom product into mole fractions here. All right. So this is your top product is also given here 4% weight by weight. So let's first convert this ZF into mole fractions. So we have ZF 30 over 46. Right. So this is 46 is the molecular weight. We have binary components here. 30 by 46 over 30 by 46 plus 70 over 18. So this is molecular weight of water. If we do this, we should get a quantity here 0.14. Now for this compositions, mole fractions, and temperature is fixed as 40 degrees centigrade, one can also obtain what you call enthalpy of this HF. We'll talk about this. Right. So similarly, let's convert this 4% of XW, which is weight by weight, into mole fraction. So that would be 4 by 46 over 4 over 46 plus 96 over 18 to make this quantity 0.016. Right. Let's say X0 is also given as 0.74 as mole fractions. So one can also of course calculate from weight fraction to mole fraction for this, the way we have done for XW and we have done for this ZF. Okay. Now we are using this nomenclature ZF because it's very important that we understand the state of this feed here. Now if the temperature is given T 40 degrees centigrade and the mole fraction is given here, one can also calculate the enthalpy for the feed to see whether it's a cold feed or it's a composition of liquid plus vapor or it's a vapor. For this problem, let's say that HF is given as 4790 kilojoule per kilomole, right, and it's a cold feed. So we will see that this line, this coordinate for this HF corresponding to this XF ZF, which is now XF, it falls below this saturated liquid enthalpy. Okay, so essentially we have marked the composition of F feed, we have marked whatever quantities are known here, XW, XD here, top product. Notice Y1 is same as XD, same as X0. We have put some specs for the vapor which leaves the top plate, and the product which is withdrawn here, the feed here, the liquid which trickles from the bottom plate NP, total number of plates, and the vapor which leaves the boiler and it arrives at number of plate NP number of plates. The question asked in this problem is given HXY diagram and XY diagram, two equilibrium specifications. Number one, total number of plates or stages, and without saying it's ideal stages. So we are not talking of any Murphy efficiency, etc. How many number of stages are required? And the question number two, what is the boiler load and what is this condenser load? So what is QB here and what is this QC here? So these are the two quantities we are supposed to evaluate in this example. All right. So what we do, we have mole fraction, everything is known. In fact, this feed is 5000 kg per hour. It's also important that we convert this feed to mole per hour. So this F is 5000 kg per hour. This can be converted into 5000 divided by the molecular weight, average molecular weight of this feed, to show that this would be a 227 kilomole per hour. So how do we get molecular weight of F? Molecular weight of F, if you know the feed composition, it's a 30%. One can make this calculation here, 30 by 48 plus 70 of 18 divided by 100 to obtain this average molecular weight as 22 kg per kilomoles. So we have converted all quantities, feed, all the weight fractions into mole fractions. Okay. Now let's look at this HXY diagram. We're supposed to plot HXY diagram. Now this HXY diagram has to be obtained for this mixture, binary component mixtures, from some handout or from, it has to be calculated from some correlations here. So for us, very often one common way of reporting is HXY diagram is a table. So we have a table which I will just note down 1 or 2 points here. Very often it's written like XY, and then you have a column for HL, then you have this HV here. So you will expect that XY, this will go from 0 to quantity like this here as 1, all right, 1.0, and you will have some number here, for this. So maybe let's say 7500, just one numbers, 48,150, maybe here we have some 9,500, etc., some number here. All right. So that's not important. More important is we try to understand that when we report XY diagram like this, then all you will do, you will choose this numbers X, so 0 to 1, X or Y, and we plot HL, saturated liquid enthalpy, and we plot saturated vapor enthalpy, HV and HL. All right. Now suppose you have chosen some point here for x and y to obtain x, to mark this coordinate HL. So corresponding to this x here, you have some HL and some HV here. So make a note that these 2 points, they are not in equilibrium. All right. So you must not understand that this is not a tie line. For every x or y, whatever numbers we get here like this, and we plot like this, these are not the tie lines. These are not the equilibrium. Tie lines would be like this. So for this y, there will be another x. For this y, there will be another x. For this y, there will be another x. These are the tie lines. That means we require one more data set for y versus x, which will go from 0 to 1 and 0 to 1. Now if we choose this x and y and mark like this, these are the tie lines. So this is y1 or y2, this is x2, this is y1, this is x1. All right. So here we are saying that for this Ponchon-Savaret methods, we require 2 types of equilibrium diagram or equilibrium information on the equilibrium. One is the HXY, and very often HXY is reported like this. You will have one row going from 0 to 1, another row going from HL, saturated enthalpy of a pure components, right, to another pure components, saturated vapor enthalpy from one component to another components. You can always go through the Perry's handbook, to obtain this HLPS. But more important here is that for any x and y, whatever numbers we choose for this, these coordinates, when you mark the vertically like this, they are not in the equilibrium. Equilibrium for any composition for liquid to this xy3 x3 has to be obtained from here. So if I choose any points here and we ask the question, this mole for a given this x2 or some mole fraction here, what is the liquid? I will go to this table, maybe do some interpolations to obtain this y, but the enthalpy, it won't be the same enthalpy as this. We'll have to look for the enthalpy for the liquid here and the liquid vapor here to obtain this on the tie line. Okay. So we have equilibrium diagram like this, y versus x. So certain mole fraction of x, this is the equilibrium. So one has to do some interpolations to plot this HXY diagram given the table like this. Of course, if you have plot like this, we can start directly from here. So assuming that we have this HXY diagram, we start now marking the distillation column. Okay. So let's plot HXY diagram again. So XY, and we have H here. We have plotted HV and we have plotted HL. All right. So we start as usual, say from the condenser. So we have the condenser here, total condenser, and the vapor composition was Y1. It gets totally condensed, we have separated, and we have 2 streams product. This goes as a reflux. We have X0 and we have this XD. Okay. So this quantity we calculated, this mole fractions, this was XD equals Y1 equals X0 equal to 0.74. All right. So this is mole fractions. The 3 compositions are the same because it's a total condenser. This product, we are saying that it's at bubble point, which means if you mark this, this would be this coordinate here on the y-axis will be HD. So this is HD, and which will be same as HL0 because part of this product is sent back as a reflux R. So we are marking this coordinate here with XD and XD. All right. Similarly, we have now this point here. So that this would be now Y1. All right. But note that this Y1 is not in equilibrium with this X0. Okay. This vapor which arrives here, we made a statement, is in equilibrium with the top plate, liquid leaving from the top plate. This would be x1. So it's in equilibrium here. It's saturated with respect to this temperature plate. So this y1 must not be mixed. This line is not a tie line here. All right. Maybe there is a tie line here which we have to read from xy diagram to obtain this x1 on this saturated liquid. This would be now x1, and the composition of this x1 will be HL1. So we have HL0 is the enthalpy of this stream which leaves here, and this HL1 is the enthalpy of the liquid, saturated enthalpy of the liquid saturated at this temperature T. So the T and Tc, they are different. You must understand this, otherwise we make a mistake in marking the enthalpy point. So this is HL1 here, and we have HL0 here. Okay. Now the problem here is given that reflux ratio was given to 1. So we have to mark del D. All right. So notice the difference, or make a note of the definition for reflux ratios is L0 over D, which is nothing but Q prime minus H G1 over H G1 minus H L0. So what is this point here? That's your H G1. So this is enthalpy for H G1. We know this Y1, we know this H G1. We know this HD or HL0, we know this coordinate here. So Q prime, Hg prime, Hg prime, HL0, they are related to this reflux ratios. Knowing 1, we can calculate Q prime here. Okay. So we do these calculations so that we can mark this del D point. So R is 1, Q dash we have to calculate, minus Hg1. If you read from this mixture, it will turn out to be that this quantity here for Hg1 is 48,680. So this is Hg1, and we have Hg1 minus HL0, 48,680 minus 39830. So the liquid which is saturated at this condensation temperature, enthalpy is HL0, 39830, and this vapor which is saturated at this temperature, their enthalpy is 48,680. So from this R we can calculate Q prime, which we said that this Q prime is the enthalpy of a hypothetical stream leaving the system at the flow rate D, but it has energy different from QC. So we had this Q dash prime. If you calculate from here, this will turn out to be as 88,510 kilojoule per kilomole. All right. So we know this coordinate. We can mark this del D, which is nothing but your Q dash prime. And this Q dash prime, if you recall, this HD, enthalpy of this liquid, saturated liquid product here. Okay. Saturated liquid HD plus this is QB or QC over D. So that's what we say, this hypothetical liquid which carries an energy of SD plus QC by D. So Q dash is known, HD is known, D is known. Okay, D we have to evaluate right now to calculate this QC. So now let's make enthalpy balance or total balance. So we have F as D plus W. We have F ZF equals D XD plus W XW. We have F HF equals D Q prime plus W Q double dash. All right. So if you see the problem statement, F we calculated, F was given in kg per hour, we converted into kilomoles per hour. XD, we know the XD mole fractions, we know XW, we know ZF, all this quantity was given to us in weight fractions, we converted into mole fractions. So from these two we can calculate D. I'll leave this as an exercise. D, for example, we get kilomole per hour, and we get W as 187 kilomole per hour. All right. So we know from these two equations we can calculate D and W. Now let's see F. We know HF is also given to us, or one can also calculate HF from this enthalpy calculation. So if we know the temperature of the feed, and if we know the compositions here ZF, one can calculate, make some balance here from thermodynamic knowledge to calculate HF. Here HF, we already calculated that quantity. So HF is known to us. HD is the enthalpy of the top product, so that is 8850. All right. So if you recall your enthalpy, the previous diagram here, we marked this point which was HL0, same as HD. All right. And from this we mark this point as Q dash, or WXT, or this Q dash. So 8850 kilojoule per kilomole. It's reflux at the bubble point, so we mark this point here. Okay. So knowing D, W, SW, one can calculate HW. HW, if you do this calculation, you should get 7380 kilojoule per kilomole. Okay. Now the question comes, we have this enthalpy diagram. Let's draw it again, and let's see what else we can calculate or we can evaluate from this HXY diagram. So we have this HV, HL. We said we know this point which is HL0. We know this XD, same as Y1. We know this HG1. Now if we know this HG1, all right, we are looking for how do we calculate or mark this del W or Q prime. Okay. So now this Q prime, we said we can write as HD plus QC by D. All right. So HD we have calculated 8850. QC we do not know this condenser load. So how do we mark this point? Now you should go back and see this definition for this reflux ratios R, which we had calculated in our previous slides. We wrote R equal to 1 L0 by D. All these points were known here, Q prime, HG1, HG1, HL0. All right. So from here one can calculate this QC. QC will turn out to be 3.16 into 10 to the power 6 kilojoule per hour. So essentially what reflux ratio was given to us, and we knew this segments. So all we do, we take the segment. That's the definition for your reflux ratios R equal to L0 by D. So if you know this, we know this. We know this Q, mark this Q point. From this Q dash we can calculate QC equal to this, because SD is known and D is known to us. All right. So either one makes use of reflux definition for reflux ratios as L0 over D equals Q dash minus HG1 over HG1 minus HL0. So if we know the reflux ratio 1, these quantities are known to us, we can calculate Q dash, which is same as from the geometry here. We can calculate, we can measure this segment by a scale, and we take the same scale here to obtain this Q dash, and from this Q dash, it's equals to HD plus QC by D. HD we just now we calculated, right? HD is known to us here, so we know HD, and HW we have calculated 7380 here. From this we can calculate condenser load, which is the first part of this question here. Let's see what else we can mark on this equilibrium diagram. So now we have to redraw this HXY diagram again, or you can still redo on the previous plot. So we have this XY, we have HV, we have HL, Okay, now we mark this point q dash, or which is del d, differential points for the top column. This is xd same as y1. Okay, now if you recall, we said that xf is known to us, so xf is given as 0.14. If we mark xf at 0.14, enthalpy was known to us. We can calculate it from thermodynamics, or hf is given, can be given to us as 4970. Now if we connect these 2 points, all right, we know this bottom product compositions, which is we calculated, or it was given as 0.016. Now this is your xf. So if you recall our complete balance which we made, feed makes an entry here. We have 2 streams living with q dash, and we have q double dash. F with hf, these 3 points f, q dash and q double dash point, they will lie on the same line. So if you apply the mixing rule, you recall this is your q dash, this is your q dash. We have feed f, enthalpy is getting distributed between q dash and q dash. We have the mole fraction species balance. For zf, we have here xw, and here we have this xd or y1. Species also distributed. All these 3 lines will lie on the same line. That means marking this point, you extend this, bring this to 0.016, wherever it intersects the composition of your bottom product as xw, you should be able to obtain del xb, or which is equivalent to q double dash. All right. Alternatively, again, one can go back and write down this species balance between these three points q dash f q to numerically calculate q dash. So I leave it to you whether for this point identification of q dash or this q double dash, either you make calculations or you make use of this geometry. You can take a scale, and reflux ratio is the same. So this segment is the same as this. That's the definition for L0 by D. You can mark this point, or you can write down. You can know the enthalpy for these 2 points. You can make use of this to mark this q dash point. From this q dash point, of course, we can get this condenser load. Similarly, once you know this point, we know this feed, we can extend this line. It will be a straight line. It will intersect at xw. This will give you q dash point, and from this one can also calculate q boiler. All right. So if you go by this graphically, this will turn out to be that this enthalpy here, which is h, or which is corresponding to this q double dash, or del xw, this will be minus 13068 kilojoule per kilomole. All right. And then if you recall, the definition for this q dash is hw minus qb by w. So here we have minus, again, this was plus qc by d. So here we have the boiler, we are giving the heat. So we had that discussion earlier. This is hw minus qb by w, the enthalpy of this stream, hypothetical stream, which leaves with this q dash. So knowing hw, all right, again here we have the boiler, this liquid and the vapor, they are in equilibrium, saturated. Okay. So knowing all these quantities, hb, w molar flow rates, q dash, which we have calculated, one can calculate boiler load as 3.82 10 to the power 6 kilojoule per hour. All right. We also say that alternatively, again, make a note of these 2 points, q dash, we have q, we have f, we have xd, we have xf, we have xw. We can apply this tie rule to write xf minus xw over xd minus xf will equal hf minus q dash over q prime q double dash minus hf. So hf feed enthalpy is known, this quantity is known here, q dash is known, that was your top product, this is q dash, sorry, this is your q dash. So this was it, top product here, q dash is known, xw, xt, xf, all quantities are known here. One can also calculate analytically. Q dash minus 13068 kilojoule per kilomole. So it's up to you whether you calculate from here, you mark the point on the graph, or directly from the graph you calculate till you get this q dash, and from this q dash one can calculate Boiled, which we did earlier, to get this hw, all right, minus q double dash into w. So it's just rearranging different ways to obtain 3.82 into 10 to the power 6 kilojoule per hour. All right. So before we do the second part of the questions, how many number of plates are there, let us summarize what we have done. So the problem statement, first you have to read the problem very correctly, and you have to realize that what is the state of your condenser. In other words, the reflux which goes back to the column. Is it a subcooled liquid or is a saturated liquid? Here the problem says that the vapor, it's the first thing is the total condenser. So entire vapor is completely condensed. Now when one condenses, one can still further cool. So if the condensation temperature is Tc, the vapor can be condensed to the saturated liquid, and one can further go for, further decrease the temperatures. So here the problem read that is the saturated liquid. That means the reflux, the coordinate of reflux HL0 or corresponding to XL0 or X0 will lie at this bottom points. Okay, so we have marked Y1, we have marked X0. So these two enthalpy coordinates are marked here. Then problem says that reflux ratio is given as 1. Now when the reflux ratio is 1, reflux ratio is nothing but L0 by D. So either from the graph you can take this segment and you can mark the second points, which is your Q dash points, or you can make the definition for reflux ratio in terms of the enthalpy, Q dash minus HF or HG1 and HD minus HG1, etc., to calculate the top points here. So either you do graphically or you solve it to get your Q dash point, the energy or the enthalpy of the stream which leaves the top product. So we mark this point here. Remember, we have not still gone into distillation column. We have not started. The first one is we have marked the points corresponding to the condenser. The top product, the vapor which arrives at the condenser, is in equilibrium with the liquid which trickles from the top plate. So that's a stage 1 that we have not got into this. All we have done, we have marked 1, 2, 3 points. Okay. Then feed composition was given. Of course, we converted all the composition which was given in the weight fraction into mole fractions. All right. So that's the first thing we have to do, because we have to realize that all your HXY diagram and XY diagram, they're also given in your mole fractions. So once we have those, so we mark your XF and HF. So you realize that this feed HF is slightly cold here. Now once HF is marked here and we have Q dash marked here, one can extend this line to get your Q dash, Q double. Again, from the graph we can get immediately, if you take a scale and connect these 2 points, we can get Q dash. Once you get Q dash, we can do more calculations. All right. Or alternatively, we wrote down the expressions for Q dash, and from there we can calculate QB, and then we can mark those points there. So either way, either graphically or from these equations, whatever expressions you have for the reflux ratios, or by applying the mixing rules, whatever you have for Q dash or Q single, Q prime, one can do the calculations, etc. Okay. Now what we do is we start marking the number of stages within the distillation column. So now we mark this HXY diagram again, or we can start from the same graph which we had earlier. So we have this X, Y, and we have this HV, and we have this HL. All right, we have already marked the condenser, so we have this XD same as Y1. Here we have this HG1, and here we have this HD. Okay, this is the difference point del XD. We have this line going through this feed, so we said that if you look at carefully, this feed composition corresponding to this ZF and the enthalpy, this feed is cold, so the feed coordinate, you will see that it will not lie on this enthalpy. Anyway, that's not important. We're saying that del XD corresponding to this HF, if we extend, then we have intersection with this XW line here, vertical line, to obtain this Q dash, which is equivalent to your del XW. So we have this Q dash del XD. Okay, so now we are talking of plates here. So we have been asked to find out how many plates are required, starting from 1, and we have this NP. All right, now we have this vapor living here, which has a mole fractions Y1, which is we have marked here as Hg1 with the enthalpy Hg1, and we have the liquid which leaves as the composition X1. Mind you, what XD is same as X0, or the mole fractions of the reflux which goes into the column. So this is X0. Y1 and X1, they are in equilibrium. Anytime we have this vapor which leaves a plate 2 with say composition Y2 is in equilibrium with the liquid which leaves is stays 2. So these two are in equilibrium. Tie lines will correspond to this X1, Y1, and the operating line will correspond to this X0 and Y1, or X1 or Y2. Or we have here, say for the third stage, we have 3, so this is X3, we have this Y3, so again these two streams will be in equilibrium, and the tie line and the operating line will give you Y3 and X2. So with that understanding, let's start from here. So this is Y1, this is your XT, and corresponding to this we have this Y1. Now Y1 is in equilibrium with this X1, so we draw this tie line. Now how did we get this Y1 and X1? You recall that we required this TXY diagram also. So we have been given two equilibrium data. One was on HXY and one was on this TXY, on XY diagram. Okay, so from here we read this Y1, whatever is the value of Y1. Okay, so this is Y1, we will get X1 here. So knowing this Y1, now we read from this graph as X1, we obtain this X1. So this will correspond to stage 1. So look at this stage 1. Vapor leaving is in equilibrium with this liquid. We have X0 same as this Y1. So first one, reflux concentration is same as the vapor which was leaving the top plate. It's a total condensate. All right. So the stage starts from here, first stage. Now we know this difference point. We can connect this X1 to this difference point. Essentially what we do here, when we connect this X1, knowing this X1, we can find this X2. That's the operating line. So if this X1, this is Y1, we obtain this Y2 or HG2. All right. So this is the way we are moving. Y1, Y2. We have X0, we have X1. Now this Y2 stage 2, it's in equilibrium with the liquid which leaves this stage 2. So again we have to come to this XY diagram, obtain this Y2 wherever it is, get another X2 here, and we mark this point. So we have to make use of both HXY diagram as well as this XY diagram. Both are in, this is mole fractions, this also is the mole fractions. So knowing this, now we have Y2 Now we obtain this point which is x2. So we are here. Again x2 and del d we connect to obtain this y3. Alright, again try to understand that from our previous discussions, for any tray which we take, say in the rectifying sections, liquid leaving and the vapor leaving, they are in equilibrium. But the molar flow rate of liquid and the molar flow rate of the vapor which arrives, alright, the two difference is always a constant here given as top product which we have as T. Similarly, the enthalpy difference between this vapor which arrives at any plate N and the liquid which leaves that plate N have the same difference given as HT. So that's what it corresponded to this difference point del XD or Q dash. So we mark that point, and whatever we connect here, the solid lines, these are now operating lines, and the dotted line, these are now stages. So number of stages 2. It marks here y3. Again we have to come back to this, see where it is y3. Corresponding to this we get x3. We connect with this, we get the second next operating line. So whatever is happening physically on this stages must also happen on this graph here. Dotted line connects the two leaving streams, and the operating line, solid line, which passes through this common point xt. Why it's common? Because the difference between the molar flow rates of the vapor arriving that plate and the liquid leaving that plate is a constant. Alright, enthalpy of this vapor which reaches this plate and the enthalpy of the liquid which leaves that plate is also a constant. So by applying this mixing rule, we have obtained this common points here. So whatever we do the calculations here, we are also getting physically on this stages. We are going from column, we are going from say liquid. If we start from the liquid, we go to the vapor to the liquid by operating, then from the liquid to the vapor by tie line, then from the vapor to the liquid by this operating. Alright, so our movement on the stage wise is like this. Let's do it again. Vapor, alright, and the liquid like this. So these are the operating lines, and the vapor which leaves and the liquid which leaves, that's an equilibrium line, that's a tie line, and this is a solid line. So one time tie line, one time solid line, we connect all these points, and it turns out to be that here if you keep on connecting, then we have one more. So we have 1, 2, 3, 4, 5, etc. Connect with this. We will get a total of 6 number of plates. So x1, x2, x3, finally we have x6, and here we have this y6, say the last. All it means, there are 6 number of complete stages, 6 number of complete stages in rectifying column or rectifying sections. So you should be able to convince yourself, if you've done graphically, that there will be 6 tie lines here. Alright, the 7th line which you connect with the solid line, what will happen if you take a tie line, this will cross this, the line which goes through the feed line. All it means, now we have arrived. Let's look at another schematics here. We have feed here, and we have this rectifying sections, and we have this stripping sections. So this is the last plate which we are saying that this is your 6th stage. Starting from here, 1, 2, dot, 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 we have the 6th stage. Vapor arrives the 6th stage, and the liquid leaves the 6th stage. Right. So this is the last stage you will get here, and the vapor which leaves here will be in equilibrium with this. So this is y6 and x6. On this graph, with the previous graph, this was your line which were which was meeting q dash and q double dash with f here, zf or xf, the feed points. You should be able to obtain 6 complete stages. 7th stages, you will see that the tie line, it crosses the big line. Now we are here. That means now we have completed your rectifying sections, and now we have to work on this W, del W. instead of del t here. All right. So if we continue with the same HXY diagram, now we have to switch. We have to step down to this stripping sections. So qualitatively, if we draw again HV, and we have HL, we this mark this point. We have this Q dash, and we have this Q double dash. We completed 6 stages here. The last one we are drawing a tie line. Now it has intersected. So that's the feed locations. Feed is in between 6 stages here, and the next stage, if we continue from here, then this would be your 8th, 7 if we leave for this feed entry. Okay, or maybe if we call this as a 7th stage, maybe this is 7th stage. So the feed enters between 6th and the 7th. All right. So once we reach this, now instead of connecting to this Q dash, now we are in this stripping section. Now we have to connect to this. Of course, this line can be solid line, can be extended to obtain the second stage. Now we are in this stages in this stripping sections, and here we have to do the same thing. Now we have this tie line, we connect here, take this liquid tie line, so that would be the stage number 8, connect with this to obtain here. Now another mole fractions, we take a tie line, stage 9, and we connect here to obtain this. This will connect finally to our top bottom product as stage number 10. So whatever operations we have done for this rectifying sections, we are doing for the stripping sections. And here we have the same mechanism, same scenarios. The liquid which leaves the plate is in equilibrium with the vapor phase. So this would be in the tie line. And the liquid and the vapor which arrives with this liquid here, this would be the solid line. So now the difference point is given with this QB with respect to the bottom product, which is your W, and the carries the enthalpy of this Q dash. So whatever, if you choose any nth plate M, the liquid vapor arriving here and the liquid leaving here, the difference between the two, enthalpy as with the molar flow rate, is conserved with the W and Q dash, which we have marked this as a del XD points. All right. So how many plates are required? We have actually, if we do it carefully, we require 10 number of stages. See, there is a crossover at this point. There is a crossover of tie line, and that's very important that we mark this point. That's the location of the feed. Feed enters just after the 6 stages which we have completed. All right. So that's the entry of the feed, and once we cross this feed, we are now in this rectifying section, stripping sections. Then we are going to connect with this, and we continue marking our data points like y1, y2, why we have this y8, so this will correspond to x8, y9, y10, x10, x9, etc. Okay. Now there is one more thing here. One can start from this point also. So instead of starting from the top product, okay, we can also start from this bottom product. We will opt once again when we cross this line here, this feed line, one has to do the calculations connecting with this top products. All right. So on this example, what we have done today, we have addressed complete distillation column, including the condenser and the boiler. All right. In the condenser, it was a total condenser, so we didn't have any theoretical stage for the top. For the bottom is always a boiler, is always a theoretical stage. So here also the last tie line which will cross this XD, or sorry, XW, will also represent the theoretical stage for the reboiler. So let's complete our discussion with the last stage here. So we redraw this HXY diagram. Now we focus on this stripping sections. All right. So this is XW, and let's say this is your del XW which you have obtained by connecting the feed, etc. Now the bottom product, when we withdraw this D, the liquid which goes out from this is in equilibrium with the vapor reflux which goes to the bottom column, bottom plate of this this column here. And here we said that this is Y Np plus 1, H Np plus 1. So this plate is Np because this boiler acts as a theoretical plate. All right. So if we start from here, we must note that this this Xb, let's correct this to Xb, bottom product, or W we had XW, and we had this HW. So these two streams are in equilibrium. So we start from here. This is, we can also start from here. This would be now HW, and now this liquid is in equilibrium with this vapor. So if we start from this side, we have the first tie line, but this tie line which corresponds to boiler. All right, and here we have this Y Np plus 1. Okay, so this boiler is equivalent to partial condenser, which we had discussed in a couple of lectures ago. All right, so the first stage we have marked this as a boiler. Now we can connect this Y Np plus 1 to this Xp. So when we are saying that we are connecting this Y Np plus 1, essentially we are connecting with this X Np. Okay, so this is the liquid composition which comes from the bottom plate Np. So solid, as usual, the definition for this operating line is that now we are connecting Y Np plus 1 with X Np. Okay, now this X Np is in equilibrium with Y Np. So again we draw this tie line to this Y Np. Okay, and how do we get this two mole fractions? Again, one has to rely on this Yx. So we have to make use of both equilibrium plot, Hxy as well as Y versus X diagram. So every time we have to read Hxy, we have to come back, take this X, find Y, or take this Y and find X here. So if you go from this side, so for every liquid Xnp mole fractions, we have to come back here, take the mole fraction, read, go like this. Unlike in the previous case where we are starting from the top, we started from the vapor, knowing the vapor compositions, etc., we got into this. Okay, so because in the top plate the vapor leaving was in equilibrium with this X1, so we had Y1 and X1. So there we started from Y1 and we got X1. Here in this case we have to start very often in the stripping sections from X1 and get this Y1. So if we do this, can you connect with this? Now again, this is a solid light. Idea is that molar difference between the two fluids is the same, enthalpy difference between the two plates is the same as your Q double dash. Okay, so if we do this, we will have 6 plates here and we will have 3 plates here. Okay, so either way one can start from here, one can start from here, depending upon the type of the problems. Okay, so this will be the end of this example here, where more or less we have been able to address entire top columns, so rectifying section, stripping sections, how to calculate the QB, QC condenser load, how to calculate this boiler load, how many plates are required. We can do the graphically. We have to be careful wherever we intersect this feed line, the connecting between Q dash and Q double dash, one has to switch from XT to XW. Similarly, if we start from here, then as soon as you cross the tie line, crosses this feed line, we have to start connecting with this XT. So this is one example. In the next class, again we will take another example where we will address certain quantities like minimum number of flux, or minimum number of plates required, or total reflux, minimum reflux ratio, etc. Okay, what is the corresponding QB and QC for those cases? Thank you.